and add in a little bit of extra stuff as well. So settle down, gents, focus. We didn't really talk about the machine yesterday. It's in the video, which I will show you later. But the machine that you put an NMR sample into has to work on with an intense magnetic field in it, the kind that you can only get with an electromagnet made by superconducting magnets, which need to be held at liquid helium kind of temperatures. So it's a big machine filled with liquid helium with a massive magnet inside it, and then the radio frequency generator, and your sample drops down. It gets carried down by compressed air into the machine in little tubes, and you have to dissolve the sample in something. So the first bit of basics that we need to cover is the solvent. So remember that any nuclei with odd numbers of nucleons in will have a residual spin, so you can't use any chemical with hydrogen in it or the proton, because you usually have much more solvent than you do sample, and it would completely overwhelm the picture. So we used deuterium, hydrogen 2. So the proton's paired with a neutron. That means the spins tend to pair up and cancel out any residual spins. So deuterium doesn't show up in a spectrum. So that gives us, the symbol, by the way, for deuterium is D. So that gives us an option of using D2O if it dissolves in water, or CdCl3, which is like a deuterated form of trichloromethane, or indeed just CCl4 if it's non-polar. It has to dissolve in that particular solvent. That's why you need a range. So you've got a non-polar solvent for alkanes and benzene and things, and you've got the standard polar solvent of water or D2O, and then CdCl3 is kind of in the middle. And then the other thing we need is a reference. So the NMR machines all work at slightly different frequencies. So you need a reference sample in there so you can compare the spectrum on your machine with a different machine from a different university, wherever it is. And the reference sample that's universally used is tetramethyl silane. So that's a silicon methyl compound, or TMS. It's usually shortened to. So TMS is popular for a number of reasons. Remember we were saying yesterday that if you have equivalent carbons or equivalent hydrogens, then you only get one peak. Well, because all the carbons and all the hydrogens, all 12 hydrogens, are in exactly the same chemical environment for TMS, it'll only give you one peak. In either the carbon-13 or the proton NMR, you're always going to get one peak. It's a fairly volatile compound, which means it's easy to remove by a bit of gentle evaporation. So if your sample was really precious and you didn't want it contaminated with TMS, you can remove the TMS afterwards. It's also a pretty inert compound, unreactive. So whatever it is that you've got to test your NMR sample, it's probably not going to react with TMS. And most importantly, because silicon isn't electron withdrawing, in fact it's the opposite, it's electron donating. When we look at our, there's no line up there, is there? When we look at our chemical shift axis, which has 0 on the right hand side, most of the peaks are going to be kind of along here, the TMS peak is going to be right over to the right hand side. In fact, it's 0 by definition. So we'll get a peak over there for TMS, and then we know what that is, and we can ignore that. We know that's not part of the molecule we're trying to identify. Okay. So just to go back over what we started looking at yesterday, we covered a couple of things. I'm going to leave them on that right-hand board because I think it's useful to have the summary of these 4 aspects of NMR. So the first thing we mentioned was that number of peaks. The number of peaks in a spectrum is equal to the number of different chemical environments that you've got, unique chemical environments that you've got in your molecule. So the carbon-13 NMR for ethanol would show 2 peaks because there's only 2 unique chemical environments in ethanol for carbon. For proton NMR, you would see 3 peaks because you've got 1, 2, 3 different types of proton. We'll come back to the proton NMR for methanol in a bit more detail in a minute. And then you have to take into account symmetry, as I was just saying about TMS, but if there's any symmetry in the molecule, and benzene is a good example here. So if I have dichlorobenzene with the chlorines in different positions, we can look at the symmetry in those molecules. How many carbon peaks do we get? Carbon-13 peaks do we get for 1,2 dichlorobenzene? 3. So I've got a line of symmetry there. So we've got carbon 1, 2, and 3, and then those are all identical. And hydrogen peaks? Try and do it without looking it up. 2, because I've got a hydrogen there and a hydrogen there, and they're identical to those on the other side. For 1,3 dichlorobenzene, how many carbon peaks? 4. So my line of symmetry is now there. So we've got 1, and then 2, 3, 4, 2, 3, and there's that. So we've got 1 there, 2 of the same, 2 of the same, and then 1 there. And hydrogen peaks? 3. So we've got 1 there, and those 2 are going to be the same. And then for the 1,4 dichloro, carbon peaks? 2, because I've got a line of symmetry there and a line of symmetry there. So that carbon is going to be identical to that one, and these carbons are all identical to each other. And then hydrogens, there's only 1 type of hydrogen. The hydrogens on those 4 carbons, they're all identical. So whether we're looking at carbon or proton, we should talk about proton NMR rather than hydrogen. Whether we're looking at carbon or proton NMR, we can distinguish these 3 molecules just simply by the number of peaks. And it's a common exam question. You'll get a molecule with a bit of symmetry in, and you just have to pick up on that. Just be careful with the, they'll have a chain of something going on here, a CH and then a CH3, and then there's a CH3 hanging off there. And because you've got a chain with things coming off it, you might not notice that those 2 CH3s, because they're both coming off the same carbon, are going to be identical. They're going to give the same chemical shift. And then that brings us nicely to chemical shifts. So you've got a list O things there. Stick that one up. The chemical shifts are given to you in the data booklet. You've probably seen them there, and, all these years, and wonder what they're for. So broadly speaking, the chemical shifts are higher for molecules which are, sorry, not for molecules. Not the molecule that's de-shielded, is it? For atoms which are de-shielded. I can't spell. De-shielded. Which happens when you've got an atom next to an electronegative group, like an OH or a carbon next to an oxygen. The oxygen withdraws electrons away. That tends to pull away the electron cloud. The shielding around the nucleus pulls some of that away and leaves us with a slightly de-shielded nucleus. And the de-shielded nuclei tend to be to the left, although there's some sort of differences there, but they tend to be the left in terms of chemical shift. So we're more de-shielded, or next to more electronegative groups as we go to the left of the spectrum. Remember that the spectrum is organized with 0 on the right and the higher number, whatever it is, on the left. It's different for proton and carbon-13 NMR. Okay, so far so good. So all of that makes NMR quite useful, and you should be able to identify number of unique chemical environments and get some useful information from chemical shift data, although a quick look at that table shows you there are some blips. For example, the alcohol OH can appear anywhere between 0.5 and 5. Now 0.5 you'd think is around about, the sort of the boring alkane, nothing special, no electronegative groups at all, going up to 5, which is more like esters and so on. So that's a big range. OH is complicated for another reason. I'll come to in a minute as well. Okay. The third important bit of information we're going to get from our NMR data, and this is just for proton NMR now. Freeze. Freeze. Excuse me a moment. We roll the batteries. Oh, it has freezed. Sure, rolling the batteries will help anyway. Give us an extra 2 weeks of battery time. Yeah, that's working better now. I'm going to go straight to the topic booklet for this. When I find it. Okay, so from the topic booklet there, we've got the spectrum for methanol, the proton NMR spectrum for methanol, and as you would expect, you get 2 peaks. The H on the OH, as I said, can appear in a variety of places. It's around about a chemical shift of 4 there. And the CH3, or the H's on the CH3, are a little bit lower. They're still fairly close to an oxygen, so they're shifted a little bit to the left there as well. So we get 2 peaks. But the important bit about this spectrum is that we get more information from that. So integration, as I'm sure you might know if you've done a bit of maths, is a way of working out the area under a curve. We don't have to do that, thank the Lord. Mathematicians have done that for us and programmed the computer so it'll do it. What the computer does is just sort of scan over the lines there and gives us a measure of the area under the curve, and then usually works out some kind of ratio for us. So the ratio of areas, I sometimes talk about peak height, but really it's area, is in this case is 1 to 3. So this gives us the very useful information that there is one hydrogen at chemical shift of around about 4, and there are 3 hydrogens with a chemical shift of around about 3.3. Now, hopefully for methanol, that's blindingly obvious that the hydrogens are in a 1 to 3 ratio. But once molecules get a bit more complicated, that ratio is going to be very, very helpful for us. So, integration gives information about, and this is proton only, the relative number of protons at each peak. Relative number of hydrogens at each peak. So there are those. Sometimes you won't get a spectrum in the exam, by the way. You'll just get a table of data like this. But you can work from there. So we've got hydrogen 1 with a chemical shift of 3.4, integration ratio of 3, and hydrogen 2 with a chemical shift of 3.9, integration ratio of 1. Note that it says ratio. The ratio is 1 to 3. That might mean that the protons are like 2 to 6 in the molecule. Okay, so be a little bit careful with that. It's giving you the simplest whole number ratio. The computer doesn't have any way of working out the actual number of protons giving rise to a peak. All it can tell you is the ratio of integration traces for each peak. So a little question in the topic booklet there. What would happen if I put in this molecule here? We've got two chlorines there. And we've got 2 hydrogens. There we go. If I put that molecule into the NMR machine, what would it spit out? So first of all, number of peaks. We're looking at proton NMR now, remember. So 2 peaks, because I've got some hydrogens there, they're equivalent, and some hydrogens there, they're both equivalent. So 2 separate peaks. Which one would be shifted further to the left? The ones on the right, because they're attached to a carbon which is attached directly to a chlorine, whereas these hydrogens are attached to a carbon which is only attached to another carbon, which is then attached to chlorines, but it's 1 carbon further removed from the electronegative groups. So we'd expect these to be shifted, these to be shifted further to the left. So if they're hydrogen 1 and they're hydrogen 2, so we'd have 2 peaks, and peaks 2 would be expected to be slightly to the left of our chemical shift scale. And then in terms of the integration trace, the ratio would be, I'll use a different colour for that. Integration trace would be, well, peak 1 would be of size, I'll make it look a bit similar. Peak 1 would be of height 3 and 2 ratio. So I'd see that 3 to 2 ratio on the spectrum there. So the peak, which is further to the left, is only produced by 2 protons. So we get that ratio. Again, hopefully that seems fairly straightforward for something like, there it is, for something like a simple molecule like this, but when they get a bit more complicated, things can get interesting. I think actually before we go on, should we just do a bit of that exercise in the back? So we did exercise 1, question 1 yesterday. Can you just have a look at exercise 2, question 2, which simply asks for you to estimate the ratio of heights of the different, I keep saying height, ratio of the areas for the different peaks. Pause. Little video. Okay, let's just run through these then. So we need the numbers are hydrogens and then the simplest whole number ratio. So here we've got 4 hydrogens which have the same environment there, and 6 hydrogens which have the same environment there. So 6 to 4 makes a ratio of 3 to 2 or 2 to 3. Doesn't matter which way you phrase it. So B is, I think everybody got this. Yeah, so we've got 6 in one environment, 1 in its own environment there, and 9 in an environment there. So 6 to 1 to 9 in any order, doesn't matter. The benzene molecule here. You done that one, Ari? 6 to 1, that's right. So I've got 12 hydrogens out there, all in the same environment, and then 2 sticking off the benzene ring there. So 12 to 2 simplifies to 6 to 1. This molecule, another very symmetrical molecule. 6, 2. We've got 12 here. Yes. And then we've got 2 here. Don't forget them. And then these 4 are all the same. So we've got 12 to 2 to 4, makes 6 to 1 to 2. Okay, and the last one, 2 CH3s, so that's 6 there, and then those 4 are all the same. So we've got 6 to 4 to 6, 3 to 2 to 3. Okay. So it's it might be that you are given a molecule like this and asked to come up with the integration ratio. It's more likely you'll be given the integration ratio as part of a question, and you'll have to incorporate it into your answer. Okay, so I've put that over there as important thing to remember about NMR number 3, and then remember that we're only talking about proton NMR now. And the last bit of information you get from proton NMR only is by far the most useful bit of information, but it can take a little bit of getting your head round. It's called spin-spin coupling or spin-spin splitting. And it's the idea that if I'm a proton sitting on a carbon over there, I've got a magnetic field coming my way, but that magnetic field is going to be affected by other protons that might be around me, because remember, nuclei behave like very, very small magnets. And so this is the one that I'm looking at on the NMR, and it's affected by this other proton, which happens to be nearby in the molecule. Of course, that proton can be in one of 2 states, right? The nucleus can be one of 2 states. It could either be spin up or it could be spin down. Because there are millions, billions, trillions of molecules in your sample, you're going to end up with roughly a 50-50 ratio of spin up and spin down nuclei adjacent to this hydrogen. Some of them will be in the same direction as the magnetic field, which will be increasing the magnetic field slightly for this proton, and some of them will be in the opposite direction, which will be decreasing the magnetic field slightly. So in other words, the local field for this proton will be slightly higher and slightly lower for that proton than the overall field. And the end result of that is that this proton will show us two peaks on the spectrum. We say it's split into two different peaks. And that's called a doublet. Yeah, who knows? I don't know who came up with this. Of course, it's quite possible that there could be two hydrogens on the adjacent carbon. Remember, this is the proton we're looking at. This is the proton which is giving the peak, but it's next to two other protons. And they could both be up, or they could both be down, or one could be up and one could be down. And of course, there's two ways of doing up and down. Think back to tossing a coin in maths lesson. You can get heads, heads, tail, tails, or you can have heads and tails, but there's two ways of making heads and tails. Which means we get four different possibilities, but two of them produce the same local field. So we end up with three peaks in a 1:2:1 ratio, and that is called a triplet. Of course, it's quite possible that our hydrogen could be next to three other hydrogens, in which case they could be up, 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 they could be down, up, up, and there's three ways of organizing that. They could be down, down, up, and there's three ways of organizing that as well. Or they could all be down. So we end up with four peaks in a 1:3:3:1 ratio. And that is called the quartet. I know when you first see this, it seems very complicated, but what it's telling us is that this hydrogen here is next to a CH3 or a CH2 or a CH. If it's not next to anything, by the way, you just get a single peak, which is called a singlet. It's not next to any other hydrogens. Which enables us to kind of assemble the molecule from bits, because we now know which bit each bit is next to. It's incredibly useful, and no other spectroscopy system gives us this information. Okay. Let's just go back to the spectrum of methanol. Sorry, spectrum of ethanol. There we go. So the spectrum for ethanol, for the proton NMR, shows us three different peaks for the three unique chemical environments: the CH3, the CH2, and the OH. The chemical shifts show us that one of the peaks is shifted further to the left. That's the CH2 though, because it's next to the oxygen. The OH, as I said, can be tricky and can actually appear anywhere around here. But that's the OH peak down there. When I do the integration trace, I get a 3:2:1 ratio, 3:2:1, where the 3, the methyl group, is hardly shifted at all because it's as far from the O as possible. The CH2 is shifted a lot more, and the OH, well, you'd expect the H to be shifted, but weird happens. And then, in terms of the splitting pattern, the CH3 here, well, the CH3 is next to a CH2. Next to a CH2, it's split into a triplet, 1 to 2 to 1. And the CH2, which is next to a CH3, is therefore split into a quartet, 1 to 3 to 3 to 1. Bear in mind that if there's a CH3 next to a CH2, there kind of has to be a CH2 next to a CH3. So you'll see this pattern of a triplet and a quartet quite often, telling you that there's an ethyl group in the spectrum. The OH, so one of the reasons why OHs are tricky is because the hydrogens in hydrogen bonding can swap very quickly. And that means that the hydrogen doesn't hang around long enough to form these splitting patterns. So in summary, OHs don't split, okay, which is why that looks like a singlet. Okay, where are we in time? We're running out of time. Okay. Can I recommend that you just go over all the NMR stuff and start looking ahead at some of the examples? I've kind of done all the teaching now for NMR. That's it. The rest is practice, and it's over to you. We will build it up slowly. Can I recommend you carry on with exercise 1, crack on with that, and see how far you get. And we'll start looking at some real spectra next time.